Good morning, good afternoon, Excellencies, distinguished guests, dignitaries, friends, colleagues, professionals, practitioners, and the large dams community. I am honored to be invited to address your conference on behalf of the International Commission on Irrigation Drainage, ICID. ICID has interest in dams and reservoirs. ICID has a registrar for historical water structures, including dams and reservoirs, and has interest in dams and reservoirs as they provide steady water supply for drinking and irrigation all over the year, protection against extreme events such as flood, guarantee steady water supply during extreme events of droughts, provides hydropower for irrigation system, abstraction pumps, dairy farming and agricultural production in general, fish and wildlife and natural healthy and rich habitat, a steady flow for the whole year, enabling us to apply integrated water management. Dams and reservoirs are of great importance to ICID as irrigation consumes 70% of the global freshwater resources. And for thousands of years, dams were built by early civilizations and have ensured adequate supply by storing water in times of surplus and releasing it in the time of scarcity, thus also preventing or mitigating floods. And you can see here a very old and ancient dams built almost 3,000 years BC. And also example here from Japan, early civilization started to build dam in a very early, really first century and even before. The current challenges that we have right now, by 2050, world population is expected to increase from 6 to 9 billion, and subsequently, the food demand is expected to increase by 100%, requiring more irrigation, water, and water consumption is expected to increase by 50%, increase global energy demand by 30 to 40%. Also irrigation, we should know that requires energy. Climate change predicted increased and reduced rainfall in different parts of the world, subsequently reduced runoff, river flow, and groundwater recharge. Also, the future climate change predicts more frequent extreme events of flood and drought. Irrigation requires a steady water supply throughout the year. And currently, there is an increase in the gap between water supply and demand. And by 2030, a 40% overall gap between global water supply and demand is expected. Do we need more dams and reservoirs to meet the challenges? To answer these questions, we need to ask ourselves, do we have adequate water supply to meet the demand now and in the future without extra dams and reservoirs? Can we cope with the climate change extreme events of flood and drought now and in the future without more dams and reservoirs? Can we meet the energy demand now and in the future without extra dams and reservoirs? Before answering those questions, let us have a look at the impact of population increase, climate change, and others on water resources. Let us have a look at the water increase impact on water supply and the demand. In 1950, the population, the global population was as small as you see now on the left, the upper left corner of the picture here. And you can see those bright circles, indication of the population growth. And from 1950, you don't really see much bright circles there, while these bright circles are on the increase from 1950 to 2000, 2015, 2015 and 2020. You can see now population has increased and that led to increase in water consumption as well. Now you can see in 1950, the per capita water availability was 12,000 cubic meter per capita. And now the availability about 5,000 cubic meter per capita. And by 2050, we expect the per capita share of water will reduce to 4,580 cubic meter. And also we noticed that in so many parts of the world that the groundwater abstraction was quite severe. And actually these aquifers are now really depleted beyond really repair. And these examples here from Crete and example from Spain, and we have examples also in the UK and so many parts of the world, including the Gulf countries. And you can see here, the Arab Emirates, Qatar, Saudi Arabia, Kuwait, and so on. All those countries, they have actually depleted the groundwater by abstraction to the groundwater beyond the level of the recharge. So climate change impact also on water supply and demand is noticed. And we have been looking at the gap between water supply and the demand in several parts of the world. Now there is examples here I will show from Italy and Cyprus and Brazil and UK as well. And this is the gap between water supply and demand that we found by studying the water resources in Cyprus. And you can see the gap is widening as we go from now until 2050. And also another example from Italy, south of Italy in particular. Now you can see also the gap between water supply and the demand is in the increase with time, whatever the scenario we applied. And in Brazil, we have seen the same gap is increasing widely with time. In the UK, we have been looking at 7 catchments from northern Scotland, like Eden catchment, all the way to south of the UK, Fowey catchment here, and those catchments we have been looking at the gap between water supply and demand. I will just show one example from the Don catchment in the Midlands. And here we can see that the climate change impact is telling us that we will have a reduced river flows in the Don catchment all the way until the end of the century. And actually that decrease in river flow is actually more noticed during the summer, where irrigation is mostly needed. Also, we noticed that the groundwater recharge, according to the climate change scenarios, is also reduced, and the recharge is also reduced on all the seasons, especially in the summertime. And we looked at the drought events, frequency and severity, and also we found that in the future, we'll have more frequent, as you see from the figure, drought events and also more severe than the current ones. And we looked at the demand between water supply and the demand and the gap. And we can also see, as we have seen in Cyprus and in Italy and Brazil, that the gap is widening with time. And actually that needs to have a solution to narrow the gap. In all 7 catchments, we found the same, apart from Eden catchment in Scotland, but all the 6 other catchments, we found that gap widening as we go over time. These are some references for publications. And how now to narrow the gaps between water supply and demand. Increasing supply, that's to meet the irrigation demand. We have some examples that we can, for example, have more surface storage of water by building new reservoirs and dams. Another option is more ground recharge. Another option to dig more wells and to abstract water, use of treated wastewater and the brackish saline water, and desalinate the saline water. However, this is maybe economically viable for cash crops, but not for field crops. There are some other solutions to enhance water use efficiency and also to use efficient irrigation system and crop selections and rotations. Increasing water supply can be done at different scales, and from really a small scale to a mesoscale to large or macro scale. So water harvesting is one way to increase our water supply. And you can see here from the scales that we started to look at harvesting water from check dams, field bunds, and so on, very small scale, to mesoscales like mountain lakes here in North Africa. And of course, we have been building nowadays, of course, large dams like the Three Gorges Dam in China. And also, we can also have underground dams, like this actually example in Brazil, where the trenches there, and they have plastic sheets to prevent water from moving from one section of the land to another and to keep the rainfall between these two sections. And also by artificially recharging the aquifer by having a different vertical shafts that would actually direct the runoff water to the groundwater aquifers and use that water when it's needed. There are some issues, of course, related to dams and reservoirs, and the main issues of concern are the safety of dams and reservoirs, societal impact during and after building the dams and reservoirs, environmental and ecological impact, impact on local climatic conditions like cloud formation, impact on downstream riparian countries and shared rivers, impact on river flows and the navigations and evaporation losses. Safety factors in designing the dams and the reservoirs is really very important. Building dams and the reservoir is not only a civil engineering construction business only, it requires good knowledge about the hydrology, economy, environment, and societies. In terms of hydrology, we need to consider the long-term historical records of flows, understand the temporal variations, and avoid using a long-term mean values if extreme events are frequent or expected. And we have two actually ways that we tried ourselves. One is to estimate accurately the volume of the reservoirs that has minimum risk and the low probability of failure by conducting probability of failure test analysis. Another thing we did as well is to conduct uncertainty analysis for river flows. The uncertainty level varies from daily to monthly to seasonal and to annual, and we got to pick up the one that we need for the safe design. And this example here for the reservoirs probability of failures, and you can here see from the figure that if we increase the volume of the reservoir to cope with extreme events, the probability of failure will be lower, and the chance of success to cope with large volume of runoff will be higher. So if we economize in the size and the digging costs, then we'll have to live with a certain percentage of probability of failure that the reservoirs or the dam cannot cope with large extreme events. And we have seen that in Brazil and in some other countries where there was overtopping. And that's because, of course, that it was not designed to cope with extreme events. And also we have been doing the probability of failure in other ways by looking at the model uncertainty and uncertainty of the flows that can actually vary from a daily to a monthly to seasonal and to annual. And here is an example of the river flows. The top one is really monthly, and the lower one here is annual. And you can see here that the CR or containment ratio here is how much actually of the observation is contained between the two levels of confidence, 5% and 95%. And you can see here the CR value for daily is 57% for that catchment. The monthly is 70%, and the seasonal 76%, and annual 85%. So if we work on annual basis, that you will have more confidence and less uncertainty, 85%. But when you work with daily values and you build your dam reservoir based on daily values, you will have high risk there because you will have high uncertainty given the containment ratio that contains about only 57% of the flows between the two quantiles, 95 and 5%. And you can see here from the generalized likelihood uncertainty estimation glue that we applied, indicated that the model captures about 70% of the observed river flow or containment ratio CR, 70% of monthly observed values are included in the 5 to 95% likelihood with quantiles. For Eden catchment, for example, we found the same. the daily values of CR 66, monthly 69, seasonal 69, and the annual 93. And you can see from that analysis, or the glue analysis, or uncertainty analysis, if now you design your dam based on daily flows, you will have a high risk. And when you apply the annual flow, you have a less, of course, risk, because it's high value and aggregated values of the days and the months, and that would give you a high containment ratio with less, of course, uncertainty. However, there are, of course, the extreme events, and extreme events, they can take place in hours. And in these hours, that you should design the dam to cope with such really a short-term high flows or high runoff. And for that reason, we might have to look at the not the annual, but we have to look at the sub-annuals, like monthly or daily values, to have an idea about what are the extreme events and how can we cope in our design with that extreme events. And these some references related to that. Sedimentation is another issue related to building the dams, and sedimentation control in the reservoir can be done by flushing, sluicing, or dredging, and by erosion control. And that's actually, all those can prolong the reservoir's life. Investment in erosion control is to be encouraged, and continuous desiltation is necessary to prolong the lifetime of dams and the reservoir. There are some issues related to the shared rivers, dams, and you can see here from, this is the task team of ICID looking at transboundary waters. And we can see here the transboundary rivers contain about 40% of the world population and 60% of world food production. And that's a very important issue. So the issues related to dams and reservoir for shared rivers requires that we should have agreement and regulations of building dams over shared rivers. And that should be in place before building dams to avoid negative impact on downstream communities. And we have actually a good example here in Europe about the Danube river, which is shared between 10 countries, and they have already an agreement came into effect in 1998 about controlling really the water supplies and also water quality, navigation, and all the aspects of the shared river. There are some societal issues related to building dams and reservoirs, and the societal impact on local communities during and after the building the dam is known by moving them to new areas with possible change in land use and landscape. Their economy and traditions are also affected. We must ensure that they are better off after the dam and reservoirs building. There are some environmental issues as well. And environmental issues related to dams and the reservoir, we noticed that in change in local climate, new microclimate due to cloud formation over the reservoir, especially if there are large reservoirs like the Nasser's Lake in Egypt behind High Aswan Dam. As a result of evaporation, those clouds they form. And also they offer a different really microclimate than what the local communities got used to. The ecological impact on wildlife, including fish and fish migration due to change in river flows, water depths, and water temperature. A balance must be struck between environmental impacts of development and environmental conservation served by development. Evaporation losses from reservoirs is another thing that we should really think about, as evaporation losses from reservoirs could be very significant. However, it is hardly accurately quantified and reduced. And when we look at the efficiencies from reservoirs all the way to the field in ICID work, we actually see that sometimes the efficiency at the reservoir level, it doesn't exceed more than 70%. So we need really to do something about evaporation losses. And there is here example of floating solar panel over reservoirs here in the UK. It's a joint reservoir between several farmers, and they cover that with solar panel to produce electricity for dairy farming and other use of farm activities. And also they release some of the surplus to the grid, the public grid, and they get money in return. And we have been using scintillometry, to measure that large scale evaporation over reservoirs and dams. And those scintillometers, they can estimate the actual evapotranspiration or actual evaporation for of the surface water of the reservoirs up to 10 kilometers. So it's a large scale, and it has a receiver and transmitter, and you can put it in one end of the dam, and the other end, you put the transmitter at one end and the receiver at the other end, and then you can measure the evaporation over the reservoirs, and you have an idea about really the value, because it is important for calculating the water balance and the storage capacity of the dams, taking into account the losses by evaporation, especially in countries where evaporation is significant. Management issues here that we need good maintenance and the operation system for dam safety. We need to regulate and control water harvesting into unauthorized reservoirs, as this negatively affects the flow to rivers and dams. And I have seen that myself in Coventry Basin in India, where anyone can actually intercept the runoff before it goes to the rivers, and some rivers like Brambadi River runs dry. Multi-purpose dams and reservoirs for water and energy security is preferred over single-use dams and reservoirs. Intensive 4 months rain, like monsoon, in some Asian countries requires a suitable design, operation, and maintenance system, and holistic integrated water supply and demand management to ensure steady water supply over the whole year. There is a need to raise awareness of the benefits gained from dams and reservoirs in terms of water and food security, society welfare, income, leisure, tourism, and the local regional economy, while safeguarding the environment and ecological services. The benefits from dams and reservoirs: we need dams. The reservoirs store water in times of surplus, and dispensing the water in times of scarcity. Dams prevent or mitigate the devastating effect and catastrophic effect of drought and flood. They adjust natural runoff with its seasonal variation and climatic irregularities to meet pattern of demand for irrigation and agricultural productivity, power generation, domestic and industrial supply, and navigation. They provide recreation, attract tourism, promote aquaculture and fisheries, and they can enhance environmental conditions. The impact of dams and reservoirs on the environment is inevitable and undeniable. If land is flooded, people are resettled. The continuity of the aquatic life along the river is interrupted, and its runoff modified and often reduced by diversions. So do we need more dams and reservoirs? The answer is yes. In the future, we will need to increase water supply by increasing green water and runoff harvesting, and store the water in reservoirs. And the reasons are: in order to meet current challenge of population increase while water is limited, we will need to double the food production by 2050. This needs extra water supply. The future climate change predicts more frequent extreme events of flood and drought. Irrigation and food production requires a steady water supply throughout the year. Energy use is likely to increase by 30 to 40% by 2050, and we need multiple reservoirs, multi-purpose dams and reservoirs to produce renewable, clean energy, hydropower to meet energy demand and mitigate the greenhouse gas generated by fossil fuel. Since the groundwater reservoirs presently tapped to provide about half of irrigation, drinking and industrial water supply are already heavily overdrawn in many parts of the world. And the only large-scale solution apart from saving water is to increase the share of surface water from storage reservoirs. Given the foreseeable depletion of fossil fuels, which presently are used to satisfy 3/4 of primary energy requirements worldwide, plus the problem of the greenhouse effect and the global warming, there is an urgent need to gradually replace them with clean energy such as hydropower, which does not release CO2. Dams and reservoirs provide water for irrigation, domestic and industrial water supply, energy production, and flood control. Other benefits include navigation, fisheries, natural wildlife habitat, tourism, and job creations. And thank you.